Okay, good morning. All right, so today we're going to look at 16.8. This is one of the big sections in this course. We're going to look at what's called Stokes' theorem. All right, so this is a theorem that relates a surface integral to a line integral. So first of all, suppose we have some kind of, in-vector field. That's a key thing here. With scalar field is really not that difficult to deal with, but in vector field, there are lots of complications with a normal vector, as you remember. So suppose you got some kind of surface. I'll draw let's do a hemisphere here. So here's our surface. And let's assume that it's got some kind of normal vector we define to be the one we want to use. And as usual, remember, typically we define the outward pointing normal to be the one that we will be using when we do our integration. Now, if you look at the curve, the boundary curve, so here's the surface. If you imagine this is a bowl turned upside down, then there's the opening is at the bottom, and then the circle around that opening, that's the boundary of that surface, right? The surface ends right there. So the boundary curve, which I will highlight with red here, we'll call that C. Now, Stokes' theorem says that when you do an integral over the surface of the curl of the gradient field. Okay, so last time we looked at how you could do a surface integral in a vector field, and now we're just going to be integrating the curl of the gradient field f along the surface. The theorem says that this is equal to the line integral of f dot dr going around the boundary curve C. Okay, so this is the basic big idea here in Stokes' theorem. Stokes says that the theorem says that the integral over the surface of the curl of the gradient field is equal to the line integral around the curve, boundary curve, f dot dr. Now we've seen this kind of line integral before. Now the tricky thing here is about the orientation. All right, so the way you figure out the orientation of the surface is very simple. The normal vector tells you that. The orientation of the contour, the boundary curve here, obeys the right-hand rule. So let me write it here. The orientation of C so you see, if n is pointing up, then the right-hand rule says that, remember the right-hand rule when you do cross product? Then you sweep around the boundary curve. It tells you the direction of the orientation of the boundary curve. Another way to look at that is that if you imagine you are walking on the boundary curve, with your head pointing in the direction of the normal vector. Okay, so normal vector defines up. Now imagine you're walking on that boundary curve, this red one in this case. What you want to see is that the region enclosed by the boundary curve C should be on your left as you walk. Okay? If you imagine this piece of paper is the surface we're looking at, the boundary obviously are these four lines. And if we say our normal vector is pointing up, and I'm walking along the boundary curve, I want to walk in such a way that the region enclosed by C is always on my left. And that tells me which direction I must walk. And that also obeys the right-hand rule. Okay? Does that make sense? Yes? Let me see some heads knocking or shaking. All right, so the orientation is very important. Surface is more or less determined by the normal vector. The C curve here depends on uses the right-hand rule. Okay, now a little bit about this guy Stokes. This theorem today is attributed to this Englishman, George Stokes, 1819 to 1903. And he did a lot of work on fluid mechanics. So all of this stuff has a very, very close relationship to a lot of modern fluid mechanics, aerodynamics. Also has a close connection to electromagnetism. However, he is not, the theorem that we're actually looking at is not entirely due to George Stokes. So we really should also be mentioning this other guy, another Englishman, Sir William Thomson. This guy lived from 1824 to 1907. Now, if the name Sir William Thomson is not familiar to you, perhaps his other name is more familiar to you. He was also known as Lord Kelvin. And you know the Kelvin temperature scale, right? This is the guy that gave us that scale. Okay, so anyway, what we're studying here is due to, in large part, to these two men that formulated and put this theorem together. Stokes' theorem actually can be viewed as a generalization of Green's theorem. So let's go back to Green's theorem just a little bit. Remember, Green's theorem says that the line integral of f dot dr is equal to this thing right here. Which, if you remember, I showed you the vector form of Green's theorem. It could be shown that Green's theorem of the partial qx minus py turned out to be, for a two-dimensional surface that lives on the xy plane, it turns out to be the same as the curl of the gradient field dotted with the k vector. Now compare this to Stokes' theorem we have on the previous page in the box. It's nearly identical except this vector k. Now in Stokes' theorem, this vector could be any vector, any normal vector, whereas in Green's theorem, it had to be k. So Green's theorem can be seen as a two-dimensional special case of Stokes. It really should be named after Thomson more than Stokes, but anyway. So in Green's theorem, surface has to be on the xy plane, and it has to be flat. Stokes allows a surface that can be oriented any way, and it doesn't have to be flat anymore. It could be the shape of a bow, it could be a cone, all these different things. But in Green's, it had to be a flat thing on the xy plane. Okay? So there's a connection to what we have seen before. All right, so let's look at that statement again. Let's figure out why this thing works. Remember, this ds can be written as the normal vector ds no vector, or d big S with a vector thing on top of it. Now you can use the definition of curl and normal and know that and actually work it out, and it'll show you it's true, this statement is true. But let's find a physical interpretation as to why this theorem works. If you remember, curl is some kind of measurement of rotation, the tendency for the field to rotate. More precisely, to cause a rotation. And this means that when we integrate that thing all over the surface, you can physically interpret that as an accumulation of tiny little vortices all over that surface. Okay, so we're just accumulating a bunch of tiny little vortices. Now imagine this is my surface. At each point, I'm going to calculate curl and then accumulate them together. So let's just imagine that we got a bunch of little curls looking like this all over the surface. Right, so that's what we're doing here. On this surface, we found out all these tiny little vortices that's given by the curl. And we look at what happens as we put them together. Now look at when two of these vortices meet. It doesn't have to be two. Let's just say, let's do four. How about four? So we got four of these things rotating in that direction. And notice that on the boundary here, like here, for example, these two are actually going in the opposite direction, right? Because they're all going counterclockwise. The top one here is going to the right when they meet. The bottom one is going to the left when they meet. Do you see that? So these actually cancel each other out. So this guy is going that way, this is going this way. there's a cancellation here. These two parts of the two vortices cancel each other out. Same thing happens here. This guy is going up, this guy is coming down. So the boundary of these two cancel each other out. And another cancellation happens here and here. So whenever these two the tiny vortices meet, parts of them cancel each other out. So the end effect of these four here really is no different than a big one going like that, right? Because all the interior parts cancel. Only the outside of the tendency of these things to rotate end up being the thing we looked at. Does that make sense? Yes? You're shaking your head. Well, because they're going in opposite directions, right? Look at this one right here. When these two meet right here, the top one is going to my right, right? The bottom one here is going to the left. And they're so close together that they have about the same magnitudes. And they're going in complete opposite directions. They cancel each other out when these two meet right here. So really only the part that comes down like that for these two matter at that point. Now look at the two at the top row here. The one on the left is going upward, right? And this one on the right is going downward. So when they meet, the boundary portions cancel each other out, more or less. So whenever these four are together, the interior parts, they wash out. And only the outside parts are the ones that survive. So these four together really has the same effect as a bigger one that's just going around the boundary of those four. Does that make sense? Okay, now look at the same thing that's with the entire surface. The same thing is happening. All of these interior parts, when they meet, will cancel each other out. So at the end, the only thing that matters is how they're going around the boundary curve. Right, so here's my big surface. And we got these things. I'll just draw a few big ones here. You get the idea. And we just saw that they cancel each other out here. The boundaries cancel. So it really has the same effect. Just going around the outside. Right? Because anything that's inside, the interior portion, regardless of what the surface looks like, all these little vortices will end up canceling one another out on the inside. And so that's why the theorem says that instead of accumulating that over the surface, we really just need to look at how the vector field is circulating around the boundary of that surface because of the cancellation happening on the interior. So this is the circulation on the boundary. So that's why we end up doing a line integral on the boundary, and that's going to turn out to be the same as the curl of f dotted with ds. Now occasionally, especially in sometimes when you look at in the context of fluid mechanics, instead of writing a C, people like to write this thing right here. And that's just a notation to indicate the boundary of S. We're calling this C here just to make things a little bit more simple and make a connection back to the line integral, but it could also be written as the little partial derivative symbol with a little s attached to it. Okay? One more important thing here before we do a few examples. Notice that this says that we only have, regardless of what the surface looks like, we only have to pay attention to the boundary. So what this says is that if two surfaces have the same boundary, C, including orientation, then according to Stokes' theorem, they will have the same value of the surface integral of the curl of the gradient field, the vector field. Right? Because Stokes' theorem says regardless of what the surface looks like, we only care about the boundary. If you have two surfaces with the same boundary, they will have the same value because of this thing right here. In other words, this cone right here and that bowl right here will have the same value of the surface integral of the curl because they have exactly the same boundary curve. Does that make sense? Yeah? And sometimes this can help. In fact, so this will be equal to that. This will be equal to that. And this is also going to be equal to just a plain old circle, right? Because that circle also has the same boundary as the cone and as the bowl. So all three of these will have the same surface integral value because of Stokes' theorem. All right? So that means that sometimes if you're doing a surface integral over a very complicated surface, you just need to look at the region, the boundary there, and then pick a surface that's very simple to deal with that has the same boundary curve. Okay, we'll come back to that point in a little bit. Let's do examples. Let's say our gradient field is yi minus xj. And S is the upper half of a sphere of radius 3. Right? Z is greater than or equal to 0. Oriented outward. That tells us which way the normal vector that we will use is pointing on that surface. Okay, so there's my surface, and our n is pointing outward. Now, if I give you this thing here without knowing Stokes' theorem, the only choice we have is to go ahead and calculate that. So we're going to have to find the curl of the gradient, the vector field, which is not difficult in this case. Right? Remember, the curl is the del cross width y minus x 0. And you can calculate this very easily. This turns out to be negative 2k. It's a pretty simple one. And we also had to parameterize the surface. And we've done this before, so I'm not going to spend any extra time on explaining why we parameterize things this way. We're just using spherical coordinate system. We've seen this before. Not difficult, shouldn't be difficult anymore. All right, so that's how we can parameterize that. And you remember that ds really turns out to be Ru cross Rv du dv. And you have to make sure it's pointing in the right way, but let's assume that we checked all that, and it turned out to be the right direction. So I'm skipping a bunch of steps for this one here because we've done this before. I'm just going to want to show that if you were doing the surface integral route, the amount of work that is expected and involved. Right, so it's easy to write down all of these things, but all of these require a little bit of calculation. Partial of this, partial of that, cross that, and this and that. Simplify trig, this and that. Much easier said than done. And then in the end, we ended up having to calculate this integral. Curl dotted with this stuff. So curl is minus 2k. 0, 0, minus 2, dotted with this guy right here, du dv, equal to dot, dot, dot. That represents maybe 3 minutes of work. In the end, you should get minus 18 pi. Okay, you've done this. You did this when you completed the assignment due last night. Not difficult to do. You've done it before. Just a lot of work. Now we have a different choice because Stokes' theorem says that instead of doing all of this stuff, we could just simply look at the boundary curve and do an f dot dr. So Stokes and really Lord Kelvin said that instead of doing all of this stuff, we could just look at f dot dr, right? Okay, so we got an upside down sphere here. The boundary I'm using red to indicate. And our normal vector points out. All right, so which way is the orientation of the boundary, the red curve here. As we look from top down, do we go clockwise or counterclockwise? Counterclockwise, right? Because remember, if you're walking on that curve with your head pointing in the same direction as that normal vector n, so you're kind of walking like this. You have to walk in such a way so that the region enclosed by C is on your left. And the only way that can happen is if we walk counterclockwise looking down. Does that make sense? Okay. So looking down, I'll stick with red here. Going this way, yoink. From 3 to, it's 3 all the way around because it's a sphere of radius 3, right? What's an easy way to parameterize that curve? It's a circle lying on the xy plane, radius 3. Yeah. Yeah. Right, exactly. How about 3 cosine t? Perfect. 3 sine t, 0. T goes from 0 to 2 pi, right? So that's easy. Very easy. dr is the derivative of that, minus 3 sine t, 3 cosine t, 0, dt. And from the last page, we can bring back our vector field, yi minus xj. So it's y here, minus x here, 0 here, right? And this y should be replaced with the y component of your parameterized curve. And then the x goes there. The x component of that goes in here for the symbol x. So this is equivalent to 3 sine t minus 3 cosine t, 0. And now f dot dr is simple. That becomes an integral from 0 to 2 pi. This guy dotted with dr minus 9 sine square t minus 9 cosine square t dt. If you factor out the minus 9, then you got sine square plus cosine square, which is 1. So this reduces to 0 to 2 pi of minus 9 dt. Okay, so instead of doing all of that surface integral, we could have done this, because Stokes' theorem said we get the same thing. And we do get the same thing. That's minus 9t times 0 to 2 pi, and that's our minus 18 pi. Okay? So in some cases, the line integral is very easy to do. In some cases, the surface integral is easy to do. It all depends on what the surface looks like and what the boundary curve looks like. We have a very, very simple boundary curve, very easy to parameterize, and very easy to differentiate. Now, if you have crazy-looking boundary but a flat surface, then the surface integral will be easier to do. So you have a choice here, and it all depends on what kind of surface or boundary you are presented with. Okay, let's look at this next example here. Here, this is one example where it's easier actually to do a surface integral as opposed to a line integral. vector field we're looking at is yi plus xzj plus x squared k. And C is the boundary of the plane x plus y plus z is equal to 1 in the first octant. Oriented counterclockwise viewed from above. Okay, we've seen cases like this before. You got a plane that slices through the first octant. We just have to find the 3 intercepts. And you just set any 2 of these equal to 0. If y and z are 0, x is equal to 1. So x has an intercept of 1. If x and z are 0, then y is equal to 1. So y has an intercept of 1. If x and y are 0, z is equal to 1. So z has an intercept of 1, right? So in the first quadrant, that surface is going to be this triangle that's kind of leaning on the z-axis. And we're told that this curve here is oriented counterclockwise if we look down onto the xy plane. So that means this guy, the orientation is going this way. If we're sticking with the line integral, then because of the sharp corners, remember we had to do a C1, a C2, and a C3, and do 3 integrals, right? You got to parameterize this, parameterize that, parameterize this, f dot dr 3 times. Not terribly hard to do, but knowing Stokes' theorem now, we have a different choice we can go with. We could do a surface integral instead. So again, Stokes / Lord Kelvin said that you can do that, that's fine, or you can do that. Okay, so suppose we made a decision to go do a surface integral instead. First thing we need to figure out is, based on this orientation of the boundary curve, which way is my normal vector going to point? Away from the origin, in other words, right? Yeah. So it's going to point this way out. Once again, looking at these 2 here, imagine if you're walking on the boundary curve, then your head should be in the same direction as the normal vector. So the boundary orientation is already determined. I have to walk this way. And if I walk that way, then my head points towards the normal vector. So the normal vector must be pointing out. So this means that we want n to have positive I, j, and k components. Right? Now you have to choose a surface. We could choose a surface. The simplest one is, of course, to use the plane. But remember, we have the freedom to choose any other surface that has the same boundary as this one here. So plane is, of course, the simplest one here, but I could have chosen a cylinder that's open on this end and it just extends infinitely to the other end. I could have done that. That would not be a very smart choice because then doing the surface integral would be a lot of pain to do. But in principle, any other surface that has the same boundary, this triangle right here, is a valid choice. Okay? All right, so if we stick with this one here, the easiest way to parameterize that is to simply let x be u, let y be v, and z be 1 minus u minus v. Right? It's already in Cartesian, and it's a kind of shape that we want to stick with Cartesian. And u is going to go from 0 to 1, and v is going to go from 0 to 1 minus u. Because if you look down on the xy plane, or the uv plane, and viewed it as a type 1 region, then xu goes from 0 to 1, and yv goes from 0 at the bottom to 1 minus x, which is 1 minus u at the top. Okay? Okay, then we need to do the partial derivatives, which are very easy in this case. 1, 0, minus 1. Rv is 0, 1, minus 1. And Ru cross Rv turns out to be 1, 1, and 1. Now, is that oriented correctly? Yeah? Yes. Because remember, based on the picture and based on the orientation of C, we wanted to point away from the origin. That meant that all three components have to be positive. And here we got 1, 1, 1. So yes. Perfect. All right. So now Stokes' theorem, Lord Kelvin theorem, said that instead of doing that 3 different lines thing, we could have done this. And here we have to do v first because v depends on u. We also have to calculate the curl, right? So you know how to do that. I'm just going to give you the end result of the curl. The curl turned out to be minus x minus 2x, z minus 1. And remember, you got to replace the x symbol with the x component of your surface parameterization. So that's minus u, minus 2u. And the z component is 1 minus u minus v. 1 minus u minus v minus 1 is minus u minus v. And then you do your integration. This dotted, so this guy dotted with this guy. we get minus u minus 2u minus u minus v dv du, 0, 1, 0, 1 minus u, minus 1, 2, 3, 4u, right? dv du. First round of integration is with respect to v, so 4u is a constant. Very easy to do. I'm skipping the details there. And ends up being minus 5 over 6. And that would be exactly the same thing if you had gone with the line integral route by parameterizing these 3 straight lines and then integrate them one at a time. You got to remember that it's not always, you don't always have to do these things one way, either all the line way or all the surface way. The key here is that you have a choice. You can choose whichever one you want to do. And on top of that, you have the choice of the surface. Any surface with the same boundary will have the same integral. Here's another example. So this one, we're just going to talk about the surface. Imagine we have a cube without a top. And assume, as usual, normal is outward. And for convenience, I'm just going to make the cube size 1, just to make things very, very simple. Okay, so there's no top. That means that this red one is the boundary. Boundary curve. And the normal vectors all point outward from each. That's a fumble. Recovered nicely. Right, so all our normal vectors point outward from each surface. Except the top, that's not the surface we're looking at. Okay? So if you do the surface integral, this one is going to involve 1, 2, 3, 4, 5 surfaces. 4 sides around and the bottom one. And that's, okay, not terribly difficult, but very inconvenient to do. If you do the line integral way, and f dot dr involves 4 line segments. On the red one here, it's not differentiable at the corners, so it involves 4 line segments. So both of these involves quite a bit of breaking things up and putting together. So neither seems like a very attractive choice right off the bat. Now you got to remember that we can look at any surface with the same boundary. So a better choice is to look at the simplest surface you can think of that has that red boundary curve. And it doesn't take a whole lot of time to think. We come up with a square sitting at z is equal to 1, right? So the simplest surface is right here. This guy right here. And the surface integral for that is very, very easy to do. X goes from 0 to 1, y goes from 0 to 1, curl dot f, all that stuff. Okay? So this is a much easier way to do. This involves the surface integral of curl dot ds for one surface only. Okay, so this comes in pretty handy, I think, on number 3 of your homework problem. You have a cube that doesn't have a bottom, or anyway, it's a cube without one of the surfaces. Before you actually get into all of these things, think about coming up with a better surface that's much simpler, that has the same boundary curve, because Lord Kelvin's theorem says that we can deal with that instead of the more complicated stuff. All right, that's it. See you Friday. Yes.